The fundamental theorem of calculus part 2 is similar in scope and design as the fundamental theorem of calculus part 1. It'll allow us the ability to do some more graphical understandings and interpretations of what's going on. And it relies on the idea of an area accumulation function. Let's start with the same example that we saw for part 1. Let's say that we're still riding along on our bicycle and we're still going at 10 miles an hour. So our velocity curve here is given by v of t equals 10. And instead of thinking of constructing the distance function, we're instead going to think of constructing an area accumulation function. And I'm going to define that function in this way. Let my area accumulation function, a of x, be the integral from 0 to x of this velocity function, v of t dt. So what is this notation telling me? So I'm finding areas under this velocity curve, and for each value of x over here, maybe I'll label this as my function a of x, and these are going to be my x values along the bottom, whereas here these are my t values. So for each x as an input, it's going to compute the area under this curve. Or dynamically, I can think of this, well, when x equals 0, I haven't accumulated any area, so I'm going to be down here at 0. And then sort of marching along, when x equals 1, I will have accumulated all of this area, which in this case is 10 units worth. It's 1 hour at 10 miles per hour. It's going to be 10 miles. So as these x values increase, I'm drudging out more area under this curve. And more area under that curve is giving me greater values, in this case, of my area accumulation function. And you can see that these areas can accumulate and accumulate, and as they accumulate, my area accumulation function gets bigger and bigger. There's a couple of things that you might want to note when looking at this. Notice that I use two different variables, that I'm thinking of these as t inputs into my velocity function, and I'm thinking of these as x inputs in my area accumulation function. And that's because these two things are actually measuring difference, that this is an integral as from 0 to x is telling me how much area is being accumulated over this span, whereas the t variable is just the input into my velocity function. It's sort of a subtle difference, but it's one that I think people have questions about and get confused about. So this is one area accumulation function, and I wrote it in green. Hopefully there's enough distinction in these colors, but I could think of a different function, right? So maybe this will be area accumulation function 1, because it's the first one that I did, a sub 1. But I could also picture starting at a different point. 0 is a logical place to start. But let's say that I wanted to consider an area accumulation function that started at 2, v of t d. Let's see what happens in this case. I know that when x equals 2, that's sort of my starting point. That's where my accumulated arrow, and I'll write this in purple. Maybe you can see over this. So that would correspond to a point down here. And as I accumulate area, as x increases, these are all considered positive areas. So as this accumulates from 2 to 3, for example, I have gone exactly 10 miles because it's been exactly an hour. And I get a curve that looks like this. Following forward, as this area accumulates, as my integral from 2 to x rolls out, as my x's increase, this function continues increasing at a rate of 10 miles per hour, or with a slope of 10. So this is my 8. At 2, I think it's easier to see what happens when I consider at a of 1. I'm going to look at this one point in particular. A of 1 is defined to be the integral from 2 to 1. So it's sort of a backwards integral, right? Usually we go from left to right. I'm moving from right to left, backwards, of v of t dt. And it means rather than 10 miles, because I'm moving backwards, I will end up with negative 10 miles in this direction. So we can think about extending this area accumulation function in either way, moving forward as positive accumulation, and moving backwards the positive values will count as negative accumulation. And the big takeaway is the takeaway that you've already seen, the relationship that we've seen a number of times now, that this area accumulation function, its derivative is going to be our original velocity function. That's the full thing that we've talked about. Let's see what it looks like formally. So formally, the fundamental theorem of calculus part 2 says that the area accumulation function, a of x, which is equal to the integral from a to x of f of t dt, and we saw a couple of different examples for a. It could be 0, it could be 2, it could be anything within the domain of this f function, so long as it's Riemann integrable. And we see that this area accumulation function is an antiderivative of f of t. Or another way to say that is that the derivative of this area accumulation function is the input function that we were integrating under. So in our previous example, we can see this because our area accumulation function, a of t, over here, if I take its derivative, it will give us this flat. The derivative of 10t is just 10, and that's the function that we were taking the area under. That's what this relationship is saying. The derivative of area accumulation function is going to be our original function that we were integrating under. Or, conversely, we could say that this a t function is an antiderivative of f of t, because that's the opposite of taking the derivative. Notice that it's an antiderivative because we have a whole bunch of different area accumulation functions that we can choose from depending upon where we start this with this value of a. Let's look at what this means graphically. And this is something that I think is a little bit harder to think through, but I think it's worth our challenge. So suppose that this is my little f of t function. It's just some function that looks like this, and I'm going to do a couple of different area accumulation functions corresponding with this as the original function. So my first a, maybe I'll even label it a sub 0 of x, is going to be the integral from 0 to x of f of t dt. So I'm going to add up all of these area pieces to correspond with these values of x down here. Here's x, here's a sub 0 of x. And as a little bit of scratch work, I can even count up what is the area. I tried to make an easy graph so that it's not hard to find the areas in each of these pieces. We see that at 0, our area accumulation function has accumulated 0 area. After we've traveled 1 unit, I'm counting up the area under this graph, value of 1, so we've made it up. Accumulating area because this continues to have positive area underneath it. So I accumulate 1 unit when I get to 1, maybe I'll fill it in. I accumulate another unit when I get to 2. And here I'm still accumulating positive areas. Even though my original, or my little f function, is decreasing, I'm still accumulating areas. I'm just accumulating them as a lesser rate. From 2 to 3, I only accumulate a half unit, 2.5. Right, so I'm still accumulating just at a lesser rate. But when I get to here, I'm accumulating areas that are under the x-axis, which I'm going to represent as negative values. So as I travel from 3 to 4, my area accumulation function is now going to be decreasing. And it decreases by a half unit because this is a half unit of area. And then from 4 to 5, I'm going to decrease by a full unit because I'm accumulating negative values, areas under the x-axis, and then I decrease another half unit from 5 to 6, So increasing, but at a lesser rate. And then at 6, my function turns, and so this value, I guess it looks like it goes all the way from 6 to 7 and from 0 to 1 are its y values, so it goes up a half unit and stops. So why did I do this? Really, this is a demonstration of the fact that my area accumulation function is going to model some of the behavior of what's going on in this function. When my little f function is above the x-axis, it means my area accumulation function is increasing. When my little f function is below the x-axis, I'm accumulating these negative areas, and so my function is going to be decreasing. And I notice that the critical points of my a function, the max and min values, are going to be the places where my little f function crosses where x equals 0. I can even write that down. The max and min values of my area accumulation function a of x are when my little f of x function is equal to 0. And notice this is the exact behavior that we would expect from a derivative. Recall, if I'm thinking of this as my function, by the fundamental theorem of calculus, we found that the derivative of my area accumulation function is my little f function. So I'm going to get a max value or a min value where my little f function was identically equal to 0. As a second exercise, I could take f function a second time and construct a different area accumulation function. It's not as nice, it's not going to line up as nicely because it's not directly underneath it, but I'll just do a few values. Suppose that I want to know what a sub 2 of x is like. So this is the integral from 2 to x of f of t dt. So this is the place where when at 2, I know that this integral is going to be 0. Direction, I'm going to add these areas. So I add a half unit of area in my first step, but then I almost immediately subtract that next half unit of area because now my little f function x-axis. I added a unit or a half unit because this area is a half. I'll start coloring it as. And then I subtract another whole unit from my area accumulation function from 4 to 5. So that's a sharper. And then I subtract a half unit from 5 to 6 because I'm still under this curve, still subtracting a half unit, 5 to 6. And I don't have quite enough space, but then I'm going to add a half unit from 6 to 7. So notice that got a little cut off. But moving backwards, although these are positive areas, because we're going backwards, I'm thinking of them as a subtraction, right? Because my integral from 2 to 1 is the negative of the integral from 1 to 2. So I'm subtracting a unit and subtracting a unit, moving backwards. And notice this new area accumulation function that I sketched out is exactly the same shape as this old area accumulation function. It's just been shifted. And that's because of the relationship of the fundamental theorem of calculus that we said that both of these are going to be antiderivatives, and it means that they could be down. The derivative of these functions, however, is always f of x.